Okay, so this thing here is a Panologic G1. It was supposed to be a thin client used by banks and insurance companies and stuff to replace the PCs on the desks and basically move everything back to the server. And so the pitch that was basically for this product was that it didn't have a CPU. So everything was done in hardware, including TCP/IP, etc. And then the magnificent thing of that was that you wouldn't have any viruses. Whatever. Now, sadly, the company went out of business in 2013. And as over time, these things became completely worthless. And so they ended up in bulk on eBay. And so I bought 25 of those for $86. Now, but really, they have all the connections of a regular PC, right? I mean, you have VGA, Ethernet, audio, USB. And so when you now start looking at the internals of it, you see a whole bunch of interesting components, but the most important one in the center is an FPGA. An FPGA is a field programmable gate array. They're less efficient than custom silicon. They're, well, less efficient in the sense that they're more expensive, but they're great for stuff like real-time image signal processing. They're also used in the world's greatest gaming monitors. And so let's see, okay. Yeah, so basically I decided, okay, these things are actually a dream for FPGA hobbyists. Because they have all the components, they're really cheap. So the first step was basically to reverse engineer the schematic. And it's really fun. You desolder the components, and with probes, you start going through like 200 connections and finding how they're linked to each other. And then the next step is basically getting those interfaces up and running. And so the first step is video out, because that's actually the easiest. And so here I have hello world. Now, and at that point, it's like, well, do you continue doing that, or are you going to do something fun? And so I chose something fun. So do you know the feeling like where you buy a new big CPU with 32 cores or a GPU, and what you really want to do then is you have this urge to basically make it work at capacity, like really max out all the performance, and it doesn't matter what it does. I think Bitcoin was invented for that reason. And so I wanted to do something similar basically with the FPGA, use all the logic and do something cool. Now, because I only had video, I was basically limited in the kind of stuff I could do. And so then the inspiration was, well, let's do something what on the Amiga and the Commodore 64 in the end of the 80s and the beginning of the 90s, they would basically make all these cool demos, and they had no purpose whatsoever, but it was just to show off stuff. Now, what have we learned yesterday about traditional rendering? Triangles, there you go. Well, what we also learned is that you need to rasterize them, and you need a frame buffer. And sadly, the hardware that we have does actually have DRAM, but we haven't gotten it to work yet. So basically, there was no DRAM, no frame buffer. Basically, that goes out of the way. So now let's go back to 1977. This is the Atari 2600. And it had some, I mean, it was the most popular console of its day, and it had some really nice games. I mean, if you look at that, that's pretty impressive, right? But some of those, I mean, the resources that were really astonishingly low. Basically, some games had only 2 kilobytes of ROM, and there was only 128 bytes of RAM. So how can you possibly make a screen like that with this low amount of RAM? Well, what they did is basically, the video chip had 2 buffers that had just enough memory for 1 line each. And they would ping pong between the two, and then the CPU would, in line with the scanning out of the video, would basically calculate the next line, and it had 76 cycles for that. And then at the end of the line, it would just flip those two pixels. And so the CPU had to always stay ahead of the CRT beam in order to be in time, and so that's why they call this technique erasing the beam. Let's now go back to ray tracing. So if we can do rasterization, ray tracing is another really cool technique. And what you do there, instead of rendering your triangles in memory, you start basically with the camera and you shoot a ray through each pixel into the scene, and then you're going to find out where does it bounce, which geometry does it intersect. You can then start shooting rays to light points and to other objects, and you can get really cool stuff like that. And what's very interesting in this particular case is that it doesn't matter in which order you render the pixels, which means you can also render them in scan order, and it means you can use it for erasing the beam implementation. Now, ray tracing is actually much better than the traditional GPU triangle rendering in the sense that you can make really physical things, but this is a little bit too complex for that little device that we have. So we needed a little bit of reductions. So this is the original paper by Turner Whitted from 1979 in which he introduced ray tracing. And so you have reflection, you have refraction, and whatever. It rendered at 60 pixels per second on a VAX 780. We want to render 6 frames per second, so we basically want like a 300,000 times faster than what this thing can do. So how do you go about implementing something like that in hardware? Well, what you always do, you start with a C model. Simple C model that basically implements what you want to do. You use it first for validation of your idea, and then later you can use it to verify your hardware against your C model and basically find bugs during simulation. So you start with a checkerboard plane like that, and then you say, okay, let's add a sphere. And then you get that, it's really boring. And then you basically say, well, let's add reflection. That should make it much more interesting. And it does, right? So now you get already something that you can work with. But when I implemented that in hardware, it turned out that not having a shadow really ruins the depth of perception. So I needed shadow as well. So let's add a light and shadow, and then we basically get this. So this was what I wanted to implement in hardware. And so what's also interesting is by instrumenting the code, you can calculate then how many scalar operations in total you need to calculate 1 pixel. And since we're going to do racing the beam, where we want to calculate a color every single clock cycle, we have to unroll all these mathematical operations into unique pieces of hardware. And from what I saw there, I thought this could fit in the FPGA. So the next step is, so initially I calculated this in FP32, the C model, and then it's, okay, how are we going to implement this? FP32 is 32 bits. It's way too big for a small FPGA. So the options are fixed point or limited precision floating point. And so I first did it with fixed point, which I got to work, and then I said, well, let's try limited precision floating point as well, which also worked. So then I decided limited precision floating point, because as we already noticed, floating point is much more interesting than fixed points, right? It's harder, but it's really fun to work with. And one interesting technique was that as I calculated, I would calculate everything in sync. And so you would see here, basically, at the end of each calculation, I could calculate the divergence between the FP32, the fixed, and the limit precision floating point. And you can basically see where are you losing precision, where are the things that are going off the rails, and whatever. Okay, so let's do a very quick walkthrough through the pipeline. So for example, this is the logic that you need for a plane intersection. You have all these scalar operations, then you have dot products and multiplications and whatever. This is not too hard. A sphere is already a little bit harder. And then when you put everything together, this is the total pipeline. It's about 115 floating point operations. The pipeline is 85 clock cycles deep. And this is actually much more useful. So this is basically the block diagram of the pipeline. You see at the top of the screen, horizontally, I calculate all the rays that are going to be sent into the scene. And then from top to bottom, you see how basically I calculate sphere intersection, plane intersection, light spot calculation. And eventually, at the end here, the text comes out. I put some overlay to put some marketing stuff. And then basically, you finally send it to the chip. And what you also see on the right is a small RISC-V CPU. And all that does is basically calculating once per frame. It calculates the net position of the camera, and that's basically it. Normally, you implement hardware in Verilog or VHDL. I used a very obscure language, Panologic, which is amazing. Because it allows you to implement pipelines and automatically balance them such that you have such a deep and complex pipeline. It's very hard to basically make all the pipeline stages use the exact result at the right time. With Panologic, you can do that. And then finally, you start implementing it, and you start with the basics, and you make it more complex and complex. And then, initially you flip the y-axis, and so your ball, instead of pointing down, points up. So that's not good. So you flip it, and you get this. And then you see here on the right, there is some weird stuff, and that's because I had made pipelining mistakes after all. So let's fix that, and then it starts looking better. And this is already pretty good. And this screen looks a bit different because here actually the ball is moving. You don't see the shadow yet because that's for in the end. So now when you look at FPGA resource usage, you can see basically I almost max out everything. Basically I have like 99% of all the slices, so those are the logic elements of the FPGA. Almost all of them are maxed out. I'm at 32 out of 36 hardware multiplication. So basically I think my goal of maxing out the FPGA, I can consider that to be done. You can see also here the floor plan of the FPGA, again, it's really filled quite well. First, some info. So basically, there's a detailed write-up on the web. Somebody took the Panologic and implemented Pac-Man on it. So what they really do, they take the original schematic of the Pac-Man console that was bought in the arcades, and they implement it in FPGA form. It's really cool, and it has the sounds and everything, and it's the real thing. And so with that, let's go to a demo. So let's switch here. And this is the only content in this conference that's 640 by 480, and it works. Thank you.